I guess. Flight of the Conchords. Cool. Okay, so let's get started. So many of you have probably used some of Google's products, and to a user, it sort of looks like a bunch of different tools and services that you can use that help you accomplish various kinds of things, looking for information, getting maps, checking your email, these kinds of things. What I'm going to talk about is a slightly different view of Google, which is more of a computer scientist view, and the sort of range of problems that we work on. I'll talk about some of the computing systems we've built behind the scenes that are used for serving all these different products, building different products on top of them. One of the things that I think is interesting about Google is that there's a really wide range of areas that people work on, and many of the products that we work on cross lots of these different areas. So from that perspective, it's a really fun and interesting place to be because you may be an expert or good at one area but not know much about another, and you can work with colleagues who know a lot about different areas, and in that way you can sort of learn more, which is always good. So I'm going to start at the very bottom, which is basically what our computing hardware platform looks like. One of our philosophies from very early on in the company was that we were going to build all of our systems on top of very low-end commodity PCs. Essentially, that's where all the volume is in the market. That's where you get the most bang for your buck. In any case, you could buy very large machines, but most of our problems are large enough that you'd have to parallelize things anyway across lots of machines. And given that you have to do that anyway, you might as well go with a platform where you get the most performance per dollar. So lots of commodity machines is what we do. In the very beginning, when our two founders were at Stanford, they started out with a kind of a motley collection of machines they found from other research groups. They would head down to the loading dock and volunteer to set up machines for other research groups, and then they kind of use them for 3 or 4 months before actually delivering them. And one problem with that approach is you end up with a very heterogeneous collection of machines with all kinds of different CPUs and operating systems. And once the company was founded, we ended up going with a more homogeneous setup made out of commodity components. We actually were pretty bold and decided we would just assemble them ourselves by buying a bunch of motherboards and disks and power supplies. So this is a very early design. What you probably can't see is that there's a tray, and on top of that tray, there's 4 machines all sharing a power supply. This turns out not to be the best idea, actually. There's also a thin layer of cork insulating the machines from the cookie tray that they're sitting on. And eventually we decided that perhaps cork was not an integral part of our computer architecture and went with a slightly more traditional-looking machine setup. We try to pack our machines pretty densely just because you use your space more efficiently. And at this time, we were renting space in data centers that we didn't own, so you were leasing space in lots of different data center providers. And at that time, the data center providers seemed to have a pricing model that charged only by the square foot. So we had an incentive to pack as many machines in as we could. So we often had to help them a little bit with cooling with a small fan we purchased at Target. The other thing we learned is that it's good to have all your connectors on the front of the machines. The previous design did not have that property, which was kind of annoying. You'd end up with crimped Ethernet cables. So based on that pricing model, we also got very adept at moving out of bankrupt data centers. So we ended up being able to move into new data centers pretty quickly. At that time, we sort of had all the racks pre-assembled. You just wheel them in, then you cable together the rack switches to a central switch for the whole cluster, and away you go. This is our current design. We've kind of gone back and forth on whether cases are a good idea. We've now settled on no sort of cases because it gives you better airflow. The cables are a lot neater than that initial design. They're all basically commodity class PCs that run Linux and a bunch of our own in-house software that I'll describe. Basically PC class motherboards. We kind of have a small number of different configurations that we use. Basically not many disks and a lot of disks. That's kind of the extent of the different configurations. Everything within one data center tends to be like the same generation of hardware, and then if we build a new data center, that'll be kind of whatever the best sweet spot is in terms of price performance for that when we build that data center. So we have heterogeneity across different data centers, but typically not within the same data center. And this is kind of our current idea of what multicore computing is. This is our facility in Oregon that we opened pretty recently. It's a pretty large facility with lots of machines in it. And that's kind of the scale of machine, if you like, that we're dealing with today. Now, one problem with these commodity machines is that if you have a lot of them, you end up with kind of bizarre problems that just happen because you have so many machines that you are bound to see almost any kind of problem. And this is thanks to one of our operations people. He put together a list of the kinds of things that tend to go wrong in the first year of a cluster. After that first year, though, it gets a little bit better. So, but you see all kinds of things that you wouldn't necessarily expect and that you really have to be prepared to deal with in your software in various ways, like a whole rack going missing. So 40 machines kind of drop off the face of the earth, and maybe just for a little while, maybe for a long time. Those actually aren't so bad. The really sort of persnickety kinds of failures are the ones that are not quite bad enough to have the machine look dead, but just kind of look very slow, or you get corrupted traffic through network switches that sort of survives TCP checksum errors and that kind of thing. So those are kind of the more severe errors where you have kind of Byzantine failures. Okay, so given that that's the bedrock on which we're building, the main issue is that you have to really provide reliability at the software level. Anything you're running on a given machine, you have to expect to be able to, that machine might fail. If you have one server, you may not really have to worry about that server failing. But if you're running something on 10,000 machines, some of them are going to die every day. And you have to really be prepared to deal with that. The other thing to note is that if you spent lots of money and bought ultra-reliable hardware with redundant power supplies or rated disks, that would help a little bit. But you still have lots of failures per day that you have to deal with. And those fancy features cost you a lot in terms of dollars for the hardware. So our view is it's better to have twice as much hardware that's less reliable than half as much that's not as reliable. Okay, so the rest of this talk, I'm going to talk a little bit about different pieces of infrastructures that we've built over the years to take a big blob of commodity machines and make them more usable as sort of a coherent system as opposed to a bunch of individual machines that you care about in an individual manner. I'll take a quick peek at how sort of when a query comes in, it gets served on google.com. I'll look a little bit at our machine translation system because I think that's kind of a fun problem. Talk about some interesting data and then give you some thoughts about our engineering style and philosophy and some of the approaches we've developed to deal with our source code base and so on. Okay, so given that you have a big pile of machines, one of the first things you want to be able to do is store data on them. And you'd like to be able to do that reliably given that machines are failing. So one of the first systems that we put together at Google was a sort of large-scale distributed file system. And this is called the Google File System, GFS. In this design, basically we just take chunks of files, 64 megabyte chunks. We're going to break files into those chunks, and each of the chunks is going to have many copies of it stored across different machines, typically 3 copies per chunk. So that if a machine goes bad, you have 2 other copies of each chunk of data that was managed by that machine that you can recover that data from, or use to make a 3rd copy now that you're down to 2. We have a centralized master in this file system that is responsible for all the metadata operations. So when you want to open a file, the client goes and talks to the master and says, okay, I want to open this file. Tell me where the chunks are, how big the file is, et cetera. And then the clients can talk directly to chunk server processes that are running on all the machines. And those chunk servers sort of are responsible for reading data from chunks off of local disk, sending it across the network to clients. One of the real advantages of this approach is all the real bulk data transfer happens between clients and the chunk servers directly. The master is not really involved in that once the files have been opened. And so you can get very high aggregate bandwidth in this file system. You can have thousands of clients talking to thousands of chunk servers and reading at many tens of gigabytes per second out of that file system. So that's sort of our lowest level of systems infrastructure that runs across a bunch of machines is a file system where you can store lots of data. It's sort of optimized for larger files than a traditional file system. We tend to, if you crawl a bunch of pages of the web, we don't put one file per page. We just dump a bunch of, millions of pages into a single file, and then we process it from there. So today, basically, GFS runs on almost all of our machines. We have a chunk server running on most of our machines. We have file systems that are many petabytes in size and can support pretty aggressive read and write loads. And the master is responsible also for making backup, like monitoring the health of all the chunk servers and making sure that the copies of the chunks that are supposed to be there are still there. And if it notices a machine has failed or that a disk has gone bad or something, it will go ahead and start making basically cloning copies of that chunk again to get it back up to the desired replication level. So essentially, machine failures are handled entirely by the GFS system, at least at the storage level. Okay, the next thing I'm going to talk about is MapReduce. Given that you have a file system, a pretty natural thing to want to be able to do is to run computations over data that you've stored in a file system and perhaps compute derived data. One example might be you have a bunch of crawled pages stored in a bunch of files, and you want to process those pages in order to, count how often every word occurs. Or maybe you want to compute an inverted index where you want to build for every word a list of documents where that word occurs. That's a pretty useful structure for the kinds of things we do when we're serving queries, is you want to be able to offline build an index like that so you can tell for the query New York restaurants what are the pages you need to consider that have the word new and York and restaurants in it. So MapReduce is a way of taking large computations like that are actually pretty simple to describe. It's not that hard to say, I want to count how often every word occurs. The problems come because you need to be able to run this computation across lots of thousands of machines in order for it to complete in a reasonable amount of time. And what we found was that over time we were ending up writing similar kinds of code all the time that dealt with a lot of the issues that MapReduce now deals with. Things like, how am I going to take this computation and spread it across thousands of machines? How am I going to get load balancing across the different machines so that I don't end up with one machine that's got a lot of the work towards the end of the job? How can I ideally move computation close to the data rather than having to transfer lots and lots of data across the network? And how can I deal with machine failures? And so MapReduce is an attempt to basically abstract the programming model a little bit and allow you to write a couple of fairly simple functions and have the underlying library take care of a lot of the details for running those functions across your data on thousands of machines. So the typical outline of something is you want to read a bunch of input data. You want to take each record, which might be a crawled page or something like that, extract something you care about from every record. You want to shuffle and sort the data, and then you want to reduce the data that you extracted in some way. Maybe you want to concatenate it all together. Maybe you want to add up counts of how often every word occurs, that kind of thing, and then you want to produce your output. So let's look at it in the context of processing geographic data, for example, to produce the kinds of map tiles that show up on Google Maps, where every image is kind of all the roads in that square and rendered as a map. What you actually get to start with is an input that is a list of features that you license from, say, a third-party map provider. And they say, okay, here's a road. It intersects with intersection number 3, and here's the path the road takes. Here's some intersection. It intersects roads 1, 2, and 5, but I don't have any data about each of the roads. So one of the first things I might want to be able to do is build a data structure that for every intersection I can tell I can basically join it with all the roads that are entering that intersection so that I have the directions of the roads. So for example, intersection 3, I want to have the actual data for roads 1, 2, and 5. And for intersection 6, I want to have the actual data for roads 4, 5, and 7 so that I can eventually render the map. So this is pretty simple to describe. It's a fair amount of data. In MapReduce, you would basically just read the input. If it's a road, you would figure out what intersections it intersects with and emit a key value pair for each of the intersections. If it's an intersection, you would just propagate the data there. And then you would essentially, in the reduce phase, have all the data for each intersection and be able to apply whatever computation you wanted to join together the complete details of the intersection, including all the road information. And so that's pretty easy to describe. It's not much code. I don't want you to actually read the code, but give you a sense of how much code you might have to write in order to be able to run this. And let's look at one more example, which is now once I've got my intersections, I want to be able to render map tiles. So the second example is in the map phase, I'm going to have a key that I'm going to designate for each map tile I want to render. So each square on the Earth, I'm going to have a square. And then in the map phase, I'm going to go through all the intersections, all the roads. And if any road intersects a particular map tile, I'm going to emit it to that map tile's key. And in the reduce phase, it's going to join together all the data for a particular map tile, and I'm going to get a list of all the roads that have any intersection with that map tile, and I can then clip to the map tile boundary and then render that road. So for example, if you know Seattle, I-5 runs north-south, so we'll emit I-5 to both of these two map tiles. The 520 bridge runs east-west, and it only intersects the top tile, so we'll just emit it to the top one. We'll emit I-90 to the bottom one, and then so on with all the other roads, and you would then end up being able to render all those tiles. It turns out that this programming model is actually pretty easy to describe a pretty broad and diverse set of problems in. And there are a lot of uses that we make of it inside Google. I'll show you some data about number of map productions people have written over time. But it's used in a really wide range of areas. Our original motivation was to write a system for building our indexing pipeline, where you start with a bunch of raw pages on disk, and you ultimately want to end up with sort of an inverted index of words to lists of documents and some other data about the documents. But there's a bunch of phases in between. You want to eliminate duplicate content. You want to maybe compute PageRank for based on the graph structure of the pages that you've crawled, and so on. So we originally wrote it for that purpose, and it's been used in a lot of other contexts as well. Underneath the covers, what really happens is that when you run a map production, you set up a little structure that says, okay, here's my map function, here's my reduce function, here's the number of machines I want to use, and here's the input files I want to run my map production over. And then there's a master that's started up and a bunch of worker machines. It could be 10, could be several thousand. And the master is going to start assigning work to the worker machines that check in with it. And one of the things it does is it tries to direct workers to read pieces of the input data that they have on local disk. So it finds out where the different chunks of the files are located on GFS. And it's going to tell this the upper right-hand worker to read data that is ideally on its same machine or at least on the same rack, so that you don't need to use a lot of aggregate network bandwidth to read input data across, say, from a different rack in your same data center. One of our precious commodities is network bandwidth, so we try to do optimizations like that help preserve that. And each map task is going to be started, which is a map task is basically going to read a chunk of the input data, apply the map function to each of the chunks, and then emit the data that's produced by the map function to a local file on local disk. And then the master is also going to assign the reduce task to a bunch of reduce workers, and each of those reduce workers is going to ask the map workers that have data for it to send their data over the network. So basically there's a bunch of RPCs that happen to shuffle the data across the network, and then the reduce workers sort things to combine together all the data for the same key, and then apply the reduce function so that you say, fine, I have this map tile, here's all the data that was emitted with that map tile key, and you can apply the reduce function to do that. And then the output of the reduce function is emitted to a bunch of files. So that's kind of an overview of the operation. When a machine fails, the master knows which map tasks that machine had accomplished or which reduce tasks that machine was assigned, and will direct all the other machines to take up the map tasks that were on a now dead machine. One of the nice things about this is we try to make the map tasks fairly fine-grained. So a given worker might do 100 map tasks in the course of a map production. And so if a machine fails, you end up losing the 100 map tasks that have been completed, but you can have each of 100 other machines each pick up one of those map tasks. And so recovery from failure is very, very quick. We actually were, at one point we were running a map production, and our operations folks, unbeknownst to us, were doing maintenance on our cluster. So we were running a MapReduce on 1,800 machines, and they were unplugging all the network switches from groups of like 80 machines at a time. So they would unplug 80 machines, they'd drop off the network, we'd lose the work, it would get redone by the other 1,720 machines, and then they'd unplug the next group as we were progressing. It ran a little slowly, but it actually all completed, which is kind of a testament to how robust this stuff can be. All right, the other thing you get by using this sort of centralized library is you get kind of a common status report about how your job is progressing. Early on, the green is kind of assigned map tasks but not completed. The red is now completed map tasks. So there's a bunch of completed map tasks in the bottom left there and some map tasks being worked on. The reduced tasks are sort of in blue as the reduced work progresses for each of the different reduced partitions. The blue kind of builds up, and that's kind of very close to the end of the job. So you get the centralized status reporting and monitoring and so on. So we originally wrote the first version of MapReduce in early 03, and then wrote another version that had much higher performance in kind of end of 03. And it's had a bunch of other optimizations and iterations done in the design as we've scaled the kinds of the sizes of map productions we've been trying to do. We now have, upwards of 10,000 different MapReduce programs in our source tree. If you take the derivative of that graph, you see that the number of new MapReduce programs per month has been growing fairly steadily. One of the things you might notice is that every summer we have a bunch of summer interns kind of show up, and they're actually, they work really hard for the whole summer, and then at the end of the summer they try to check in all their code. And so we end up with a big spike towards the end of the summer of when they're going to check in all their code. And it's kind of, most of these interns don't have a lot of experience in writing large, scale, high-performance distributed computations, and they're still able to sort of make use of MapReduce to run jobs on lots of machines and get work accomplished, which is kind of the whole goal. Is you want to be able to have this infrastructure that takes care of a lot of these details for you, so you can concentrate on what it is you're really trying to do rather than dealing with machine failures. There's just some statistics over time of how much we've been using MapReduce for various things. We now run about 100,000 MapReduce jobs per day, and they use on average 400 machines each, roughly. A lot of machine years used in September. The jobs complete pretty quickly, about 5 or 10 minutes or something, even though they're running on lots of machines. So it's been pretty heavily used and has grown in utility and sort of its integration into our source base over time. Okay, let's switch gears a bit one more time, and the first of many. Let's talk about a system called Bigtable. So Bigtable is a system that we started working on a few years ago to allow us to have a slightly higher level view of data than a file system. It's kind of like a database, except it doesn't do sort of relations or joins. It's really designed for semi-structured data. We have a lot of that kind of data at Google. So we have, for our crawling system, it goes out and fetches pages, and we have different kinds of data about every URL. We have sort of meta information like when did we last crawl this page, what happened when we tried to crawl it, did we get a success code back, or did we get a 404, that kind of thing. We have the actual contents of the page, which are pretty big. We have information about the links from each page. We have kind of the inversion of that, which is what are the links that point to this page. We have PageRank, which is kind of this offline graph computation we run and want to be able to update and get data. Similarly, we have per user data where users want to be able to set their preferences of what their preferred language is, what are their recent queries and search results so that we can show them their history. And more recently, we've been dealing with a lot of geographic kinds of data. And in particular, satellite imagery is a fairly large, bulky kind of thing. So in all these cases, the scale is pretty large and many, many terabytes or petabytes in many cases. And we want to be able to have pretty high volume access to it. So one approach would be to use a commercial database of some sort. One problem with that approach is that the scale is pretty large, even for the pretty high-end commercial databases. And even if it weren't, when you have a really large-scale database that you need to use, the price that you pay is often quite high for commercial databases. So by building this system internally that was more suited to our needs and a little bit more tailored to our needs, we can also then amortize the cost of building it across lots and lots of different projects. And once you've built it and can use it for 10 projects, the 11th one is pretty easy to use it for and has a very low marginal cost. The other thing is we can integrate a lot of low-level storage optimizations into our system that would be hard to do if you're running on top of a commercial database layer. We do a lot of compression inside our system, even across different rows. We're integrated pretty tightly with GFS so that we can give hints about placement of where chunks should go so that we can get locality. And another reason we decided to build it is kind of fun to build things like this. So the basic data model that we provide for Bigtable is essentially a distributed multi-dimensional sparse map. So what do I mean by that? You can think of it as a triple that maps from a row and a column name and a timestamp to some cell contents. And the cell contents we just treat as an uninterpreted binary stream of bytes. So the rows typically, in one example, if you wanted to maintain data about URLs, the row name would be the URL. We might have a column for the contents. We might have another column for, when was the last time we crawled it, another one for the page rank of the page. We found it useful in our systems to maintain historical data, to keep multiple versions of a particular row and column so that we can look at how things have changed over time or look at various trends. And that three-dimensional model seems to be a pretty good match for a lot of applications that we want to build. Let's see. So the way we actually implement this system is the row names are sorted. And so when you create a new table, it essentially starts out with a bunch of empty rows. And as you add data to it, you have a bunch of rows and columns. A column doesn't have to exist, and so it doesn't exist until you actually write data into that column. Over time, you'll end up filling up the data. And one of the important properties we wanted was the system should be largely self-managing. So if I start adding more and more data to the system, I don't want to have some heavyweight sort of manual process whereby I say, oh, gee, now I need 200 machines instead of 100 to maintain my data. I want the system to be able to sort of automatically adjust to more data, or maybe I can throw more machines at it and have it automatically adjust to more machines, even if I haven't added more data to the system. So the main way we deal with that is the unit of serving is something called a tablet, which is essentially a contiguous range of rows in this large table. And a given table may be made up of lots and lots of tablets. When you add more data to a tablet or to a table, eventually a tablet will fill up and we'll decide it's too large and we want to split it into multiple pieces. Two, actually. And so we'll pick a row that's roughly in the middle of the size profile of the different rows in the tablet. And we'll just say, fine, we're going to now split apart the state that was maintained in that system. And now we have two independent tablets, and those tablets can now be moved around the system, and responsibility for serving those tablets can be moved from one machine to another. So the representation of a tablet is basically you can think of it as a infinite length log that we truncate periodically by checkpointing the state into a a special file format we call an SS table. It's basically just a key to value map, where the keys are basically combinations of row, column, and timestamp, and the value is the actual bytes there. So when you get a write, you append to a log that's stored on GFS, and you also represent that write in memory for a little while so that you have fast random access to recently written data. Eventually, your memory fills up, and you decide to dump it to one of these files on disk. So you find the tablet that has the most buffered updates. You dump it to an SS table on disk that's going to represent a range of that log, and then you can then truncate the log and remove the prefix of the log because you now have a representation of the data in the SS table file. When a read comes in, you essentially look in your in-memory buffer, and you then also maybe look on the on-disk SS tables, doing a seek for that particular key that you're looking for. You may need to look in multiple SS tables. We also allow you to specify that certain columns essentially should be mapped into memory. And so those SS tables get mapped, and you can do very fast, high volume operations on data mapped into memory. Maybe you go directly to memory in some cases, skipping the on-disk ones. So like a lot of our systems, the structure of Bigtable is that we have a centralized master, and then we have a bunch of servers that are going to be responsible for actually serving data. Underneath the covers, we have, sitting underneath this, we have GFS, where all the state for Bigtable is stored. So all the SS table files and the log files are written into GFS, and when a tablet migrates from one machine to another, that other machine will read whatever state is needed to recover out of GFS. We have a cluster scheduling system where we can say, I want to schedule a job that is my tablet servers with 400 instances for those, because I want to run 400 tablet servers, or you can change it to be 500, and then the master will notice that now there are 500 tablet servers and sort of rebalance the serving state. We also have a lock service that we use to do master elections, so that we only have a single master running that is making decisions on the cluster. I'm not going to talk much about that. And then we have a client library that we link into our applications that when it wants to open a file, it talks to the lock service to find out where the master is. When it wants to read and write data, it talks directly to the tablet server. And metadata operations like creating a new table go to the master. Pretty straightforward. The status of this is that over time, kind of like MapReduce, we started out with a few applications in mind, some that were fairly latency sensitive, so we were actually serving real user requests behind some of those applications, and other ones were more batch style crawling system kinds of things where you just want to have a large repository of data and have it in a slightly more structured format. And over time, the number of applications that are using this system has grown a lot, and we now do satellite imagery processing in Bigtable. We do ORCID is served heavily off of Bigtable. All kinds of things use this kind of as a low-level building block for building their applications. And we have, the biggest cells tend to have several thousand tablet servers running, managing, many petabytes of data, and shuffling data around to balance load and so on, dealing with machine failures. So again, a given machine is responsible for serving many tablets. So when a machine fails, the master notices this, and recovery is very fast because we end up taking the 100 tablets that were served by that machine and having each of 100 other machines each pick up responsibility for one of those tablets, and they each recover in parallel the state, so that within a second or two, typically, you can recover all the serving state of a particular machine if that machine dies. Let's see. So the three systems I've talked about and a bunch of other ones that I haven't talked about, mostly they're a particular instance of GFS or Bigtable tends to run within a single cluster of machines. They don't tend to run across a really wide area, so we don't run a single Bigtable cell with half the machines in Atlanta and half in Oregon. We would run multiple Bigtable cells. We do have a replication system set up so you can kind of keep Bigtable cells in rough consistency. So writes done in Atlanta in one Bigtable cell can be propagated to a different big table cell in Oregon. You can kind of configure that. But one of the things that we've really noticed now is that we really want sort of our next generation infrastructure to be a system that runs across all of our machines or a large fraction of our machines rather than having separate instances. So one of the advantages that would give is we would have a single global namespace for all of our data. Right now, when you put files in GFS and in one cell, and then you copy those files to another cell, they have different names, like it's GFS/Oregon and GFS/Atlanta. And we've lost the association that those files are the same and are meant to be, copies of each other. So what we really want is to have a single namespace where you can add replicas of particular pieces of data, but keep the fact that that data is the same. We'd also, in some cases, like stronger consistency across different data centers. Right now, the big table replication system gives you eventual consistency. So if a data center is partitioned and then that partition is healed, all the writes will eventually propagate. But in the meantime, you have kind of weakly consistent semantics. We'd also like to be able to say things like, this data is important. I want it on 2 disks in Europe, 2 in the US, and 1 in Asia, and I don't really care which particular data centers it lives in. One of the big problems we have is because we run so many individual GFS cells or big table cells, and humans have to make a decision now where they're going to store their data. And when they want to change which GFS cell they store their data, that's kind of a less automated operation than you might like. So the design goal of our next generation systems is that we want to be much more automated in how systems run across different data centers. We're pretty automated at the within cluster level, so machine failures and all that kind of thing are taken care of pretty well by our existing infrastructure, but across clusters and data centers, we're not as good as we might hope. So we want to be able to automatically move jobs, move data, automatically shrink and grow capacity of jobs as request loads change and so on. Okay. I just have one slide on this. I figure everyone's kind of curious about what happens when a query comes into Google. So one of the things that sort of may not be obvious to many people is that there are a huge number of subsystems involved in processing that query. So when a query comes in, it's routed by our front-end networking hardware to a particular web server that's going to kind of coordinate the whole process for getting the results to show for that query. And initially, the system was relatively simple. We had kind of index servers that have an inverted index of the documents in our index. So they map from, for a subset of the documents, they each have a local copy of an inverted index, which is for each word, what are the documents that occurs in, and maybe some other per document data like how important is this page or various other kinds of things. And so when a query comes in, you send a request to one copy of each of the different partitions of the index, those 4 lines going to the I0 through IN things. And you have many replicas of each of that piece of index data so that you can handle the query volume. And some of this is showing one data center. You might have many other sort of replicas of this entire setup in different data centers. And each of these local index shards computes what are the best results for this query for its subset of the documents. So given the query, say, New York restaurants, it'll compute what are the best results for its few million documents, send back the results of the top 5 or 10, and then you essentially merge those results by score across all the different pieces of the index, and you figure out what are the results you actually want to show as the top 10 results on the result page. Once you figure that out, you essentially are just getting identifiers of the documents back from the index system, and you need to then send the request down to what we call doc servers, which are responsible for taking that identifier and the query and computing the little summary of the page, the title, and the snippet for the page. One thing to notice is that the snippets we compute are query sensitive. So if I do a query New York restaurants that matches a page, that may be a different snippet, even for the same document, for some other query that matches the page. In the meantime, there's a bunch of other systems that are involved in processing the query. We added a spelling checking system a long time ago, an ad system, and the ad system itself is composed of lots and lots of different components. Over time, we've been adding more and more different kinds of corpuses that can be searched, like news, different books that we've scanned, blogs, various kinds of things like that. And we now, sort of in parallel with the request to the main web index, do requests to all those other corpora and try to show those on our results page if we think that a book result is appropriate for this particular query. That's actually an interesting problem, is how can you figure out for this query what results you want to show and from what corpora make the most sense. Okay, switch gears yet again. Let me talk a little bit about our machine translation system, because there's some interesting systems problems behind that. So the goal of machine translation is basically you want to take text in one language and translate it to text in another. And you want to do that in a way that gives you as understandable as possible a translation. So the approach that a group at Google is using is called statistical machine translation. So machine translation is not really a new concept. It started many, many years ago, I think in the 70s, with a rule-based system where you say, for this word in English, I'm going to translate it to this word in French, or maybe this phrase. And over time, you build up more and more rules that allow you to do better and better translations. The statistical approach is completely different. Basically, you start with a bunch of training data, and there are two main kinds of training data. One is called parallel aligned corpora, where I have a bunch of text in one language and a bunch of translated versions of those sentences in the other languages. And I build a statistical model that says, okay, I see this English sentence, and then I see the corresponding French sentence. I'm going to compute statistics over all the words and phrases that I see in those sentences, and I'll come up with a model that says, well, if hello is in the input sentence, then with probability 0.87, the word bonjour is in the corresponding French sentence. And so you essentially get a model of word by word and phrase by phrase replacements. The other thing that's really helped a lot in recent years is the ability to have what's called a target language model. Because the problem with it is you can't get much in the way of parallel aligned corpora. There just aren't that many corpuses that have really huge amounts of sentence by sentence translations for all language pairs. But one of the things that can really help is if you use the parallel model to generate a bunch of candidate translations, and then you can use the target language model to pick the most natural sounding ones of the candidates. So let me give you an example. Let's say I have two candidate sentences that are translation candidates, and I want to pick the one that sounds the most natural. I'm going to look up each 5-word sequence in a target language model. And if I find that this 5-word sequence has occurred in all of our English documents 3 times, and this other sentence has a 5-word sequence that's never occurred, it's more likely to be that I should go with the one that's occurred 3 times. So the more data you can train the system on, the better it's going to be. So essentially, you end up wanting to build these target language models on really, really large amounts of text, basically all the documents we can get our hands on. And so you end up with a relatively large model, even after you've just summarized it by counting how often every 5-word sequence occurs. And it turns out that the translation process needs to actually look up data in this model quite a lot, unfortunately. Like 100,000 to 1 million lookups per sentence that you want to translate. And the model is 1.5 terabytes in size. So in typical fashion, we just spread it across a bunch of machines and do lookups. So it seems to work pretty well. And one of the things that target language model really helps is the translation quality. So this is a competition that's run annually, or every few years, I guess, by the National Institute of Standards. And it has a bunch of competitors submitting their machine translation systems. And the y-axis is the blue score of how good the translations were on some test data set. And Google did quite well in these competitions. We can think of the blue score as sort of the fraction of overlap of the translation system with a collection of human translations of the same documents. And it actually doesn't really go to 100, because even if you had another human translate it, it wouldn't give you 100%, because they tend to translate things differently as well. So let me show you a non-Google translation system that's available on the web. I won't say which one. And you can kind of try to read those middle paragraphs. It doesn't flow real well, I would say. And here's the same text translated through Google's Arabic to English translation system. And what you see is the impact of having a really large language model makes the sentences flow a lot more naturally. So if you read those middle two sentences, they're not perfectly grammatically formed, but they're a lot better than the other system. And as you might expect, the more training data you use for your target language model, the better your BLEU score is going to be. And so roughly every doubling of your training size for your language model gives you a little bit higher BLEU score, which is kind of cool. So more data is generally good, which is in part why we've been focusing a lot on building infrastructure to process large data sets and do things like compute a new language model fairly quickly, or try out different things in how we apply the language model to translation, or any of 100 other things, because the quicker you can turn around these kinds of experiments, the quicker you'll be able to sort of improve things. Here's just another example of having the right tools makes it so people can kind of ask questions. So someone at Google who worked in our book scanning group said, gee, it'd be kind of cool to know where different locations were mentioned in books and how that's changed over time. So they essentially, took all the scanned books we've scanned, I think more than 1 million books today, figured out, applied a geographic place name recognizer to all the text, took the extracted locations and plotted them by year the book was published, and plotted the density of how often those things were mentioned. And it's kind of interesting data. It's heavily biased towards English books because we tend to scan more English books than other kinds of books, but you can sort of see the expansion from Europe to the rest of the world in terms of the publishing industry, at least. Kind of fun, and being able to, take questions like that and in a couple hours have a rough cut at that data is kind of fun. So let me switch gears a bit again and talk about some of our software engineering approaches for managing our source code base and our projects as Google has grown over time. So one of the things that I think is interesting for a company our size now is that we still have one large shared source base. So we have thousands of developers working on the same source code base. There's a lot of lower level libraries that are used by almost everything. There's a bunch of higher level libraries that are shared across multiple projects that are kind of doing similar kinds of things. And then there's a bunch of application specific code. Now, one of the big advantages of having this single repository is that improvements in this core library benefit everyone. You don't have this sort of splintering effect when you break your code into multiple repositories and then break things into different groups, and those groups then kind of stop talking to each other and just work on their own source code and polishing their own libraries, and you don't get the benefit of those libraries sort of benefiting everyone, but they benefit just a small subset of your engineering group. So that's one of the main benefits, and it's also easy to find example code of how is someone using this library function, or what's the best way to count how often different things occur. Can I find a MapReduce that does close to what I want, and maybe modify it, or at least look at the code and see how they're doing it. So that's a pretty huge benefit. There are, of course, some drawbacks, which is that you sometimes have these kind of tangled dependencies, as instead of just looking at some piece of code, someone has said, oh, well, I'll just, I'm in Blogger, and I'm going to link into the middle of the book scanning project and use their library for doing this because it does exactly what I want. And that happens. One of the things that we found pretty essential is that it's really helpful to be able to quickly search all of our source code. So one of the things I did a few years ago was built a little internal tool that's not particularly fancy, uses a lot of machines. You just spread the data over lots of machines, and you just can run basically grep and parallel across all of our source code. So within quarter second, you can search all of our code and find examples, uses. It's very helpful if you're maintaining low-level libraries so that you can find everyone who uses this routine. What if I change the semantics, or what if I want to add an argument? What would that do to all the different call sites of this routine? So that's pretty helpful. We have pretty disciplined software engineering practice, so we tend to do every piece of code that's checked in is code reviewed by at least one person. We do a lot of design reviews before writing a lot of code. Lots and lots of testing. Testing is done for individual modules, larger tests for whole systems. We have a continuous testing framework that is always running all of our tests. Most of our development work is done in C++, Java, and Python. And the way it kind of breaks down is anything touched by, say, a web query is done in C++, and a bunch of other things as well. Java tends to be used in lower volume applications like the advertising front end that advertisers log into to get reports and so on. That's not quite as performance critical as the code that runs on every web search, and so that tends to be done in Java. Parts of the Gmail are done that way, and Python tends to be used for configuration and so on. The other interesting change over the last few years has been we've moved from being a Mountain View only engineering organization to one that has many, many, many engineering sites all around the world in the last few years. And the motivation for that is obvious. You somehow can't convince everyone in the world to move to Mountain View. And so you want to hire really good candidates regardless of where they actually are living. And so we've opened up engineering sites close to where we think we can hire really good people. There's obviously a bunch of issues with having lots of small and medium-sized offices is that you need more coordination of who's doing what. Communication is harder. You can't just kind of bump into people in the hallway. And establishing trust between remote teams working on the same source code base is sometimes tricky when you just haven't met someone face-to-face. But we've developed a bunch of techniques. First, we put all of our documentation and source code online. Source code is obviously online. We tend to use video conferencing and email a fair amount. Careful choices of who's going to work on what tends to make it so that you can try to break things at the sort of minimal communication cut boundary so that this group can define an interface to the spelling system and can go off and work on it, and these people can use the spelling system through that fairly narrow API, and the spelling system folks can roll out new releases whenever they want without a lot of coordination with everyone else. And that helps a lot. The Big Table project is split across 3 sites. I tend to work pretty closely with someone in New York, with actually an office of people in New York, and we actually just have a permanent little portable video conferencing unit permanently hooked up to their office, and we just keep each other muted all the time. And you can kind of unmute and say, hey, I'm thinking of changing this code. It's actually better than having an office of 6 people is to have 2 offices of 3 people in different places because they're very quiet, at least when they're muted. And I think, one of the things that I really like about Google is that it's a really fun environment to write software. There's a really interesting range of problems and people who have different ranges of expertise. You can learn a lot about other areas. For example, the machine translation system, I didn't know anything about machine translation, but I knew they were having some issues with how can they do lookups in this large language model. And so I went off and worked with them for a little while in building this large language model serving system. And I learned a little about machine translation. They learned a little about how to distribute computations across lots of machines. And the end result is something that probably neither one of us could have produced alone. So it's fun. I obviously covered a lot of ground, not much in depth. So there's a bunch of papers and other papers available that have a lot of details about some of the systems I talked about. And I'll take any questions. Yeah. Oh, yeah. Is there I guess there's a microphone for questions there. Now you're third in line.
Let me just ask you. You mentioned about the masters and the slaves. Are you using any special hardware for the masters compared to the slaves?
No.
It's the same.
Yeah, it's basically our scheduling system will pick 101 machines, one of which will be started up as the master, and 100 of which might be workers.
Okay, so same hardware.
Same hardware. It makes things simpler. If you end up with a small number of machines that are very specialized for masters, it's kind of an operations nightmare.
Google's pretty good about scaling across a bunch of distributed machines. How about scaling kind of deep down into the new multi-cores that are going to come out? Are you going to do anything special or just follow the commodity path?
Well, we really, really like multi-core machines because we've already had to parallelize our computations across lots and lots of machines. And essentially, to us, multi-core machines just look like lots of little machines with really good interconnects. And so from that perspective, I think it's relatively easy for us to use multi-core machines because we're already sort of used to parallelizing things, breaking things, and running multiple threads anyway. So yeah, multi-core machines are great. We're very happy because single thread performance doesn't matter to us at all. Well, not completely at all, but to a large extent, we have lots of parallelizable problems, and we're totally happy breaking them up.
I have a question about overall architecture. There seems to be a trend nowadays. If you talk to vendors like Sun, they tell you to go get a blade system, and the blades don't have disks on them. And then they talk to some other kind of disk system over here. Do you think that's a mistake, in your opinion, to go that kind of separated architecture?
Well, I think, I guess you're talking about storage area networks or, fiber channel-based disks or something where you can access them from multiple machines.
All the Google stuff seems to say, okay, do the computation and the data in the same place.
I mean, I think those systems have their place, but for example, if you're running a commercial database and you need a really high-performance disk system, you might buy one of those because that's a really easy way for you to get a high-performance disk system that can run underneath a commercial database. But in our case, we're pretty happy using cheap disks attached to lots and lots of machines because you get a lot more spindles for the same price, you get a lot more disk storage capacity for the same price, and you get a lot more computation near your disk for the same price. So if you're willing to build things yourself or use open source versions of things like the Hadoop project has an open source MapReduce and an open source version of GFS. Those kinds of things, I think, can make it possible to use the techniques that we use on lots of commodity machines and not buy into a large, storage area network, for example. So, but obviously, you have to evaluate what makes sense for the kinds of problems you're trying to solve.
Speaking of that, some of the problems you described, including distributing it over a large number of machines, seem to be pretty unique to Google. And especially the solutions seem to be pretty unique to Google. So you can't buy a commercial database like Oracle, and you have to have your own file system. Does that create a challenge in terms of being able to train new set of recruits? How long does it take for a typical programmer to join and be productive and come up with a new application?
Right. So I think one of the things that we've done a pretty good job at is because we've been hiring quite quickly and growing pretty fast, we've had to create a lot of online documentation and sort of initial training material to teach people about the systems we built. And I think we've done a pretty good job of that. So when someone is hired, they go in and can pick and choose from a collection of like 10 or 12 kind of half-day courses and about how to use MapReduce or how to use GFS or how to use our source control system, that kind of thing. And so I think we've gotten pretty good at bringing people up to speed relatively quickly. That said, there is a lot of stuff to learn when people join, and I've heard new people who are fairly experienced when they join say, wow, there's a lot, it's like drinking from a fire hose kind of thing. But, I think the desire to just jump in and learn stuff is the main thing that will keep people above water. Okay. I gather we're out of time. I'm happy to hang around in the hall and answer questions if people have them.
So the answer is